So the next topic is approaches toward congestion control. As we mentioned before, because currently we use packet switching, so we have several different routers are interconnect with each other, and each one has a buffer, right? So, but actually router is very busy, so they are busy in forwarding or do the routing task. So basically, the router cannot explicitly tell the sender to send faster or slower. Basically, we don't have such kind of mechanism in reality. So the sender should come up some mechanism to realize that the internet is congested or is not congested. Okay, but ideally, routers should tell the sender to slow down or something like that. But actually, we don't have such kind of mechanism. So in the following view graph, we will talk about how a sender to make a guess, to infer, okay, what is the current condition of the routers? It is congested or it is not, okay? So TCP will have certain different mechanism to do such kind of congestion control, okay? We'll skip this view graph because we'll talk about more details later, okay? So right here, the TCP congestion control has a mechanism called AIMD. Additive increase, multiplicative decrease, okay? The approach is like that. Sender can increase sending rate until packet loss occurs. Packet loss indicate congestion, and they decrease the sending rate on loss event. So take a look at it right here. Sending rate. That is the senders, right? Senders. At the first place, okay, the sender will send certain amount of packet to the internet and see if all the X comes back. If all the X comes back, and that means that amount of sending rate or that amount of in-flight packet is okay to the current router status. And we incrementally increase the sending rate, for example, right here. If the network still good enough to accept higher sending rate, then the X will goes back to the sender, right? But at a certain moment, if the sending rate is too high, so the buffer keep start drop packet, and at the sender side, it will receive duplicate egg, right? That is because some of the packet get lost, or even worse, the sender did not get any acknowledgement. That because of the packet get lost. Then the sender can decrease its sending rate. So that because if you even add more packet, in-flight packet to the internet, it is useless because all the packet has been dropped it. So at that moment, you should decrease your sending rate so that the routers can digest the packet in its buffer, right? It can send the packet out. So you should not send more packet to the network right now. You should decrease your sending rate. Okay, and after that you can keep trying. Okay, so I said that it is a try and error process. Okay, so every time, right here, so every time you get an egg, you get egg. Every time you get an egg, you increase your sending rate by 1 maximum segment size. Every time, every RTT means every round. Okay, we'll talk about it then too. Until loss detected, that is it. And every time the sender experience a loss, and you cut your sending rate in half at each loss event. So that is called AIMD. Okay, AIMD. So that is the way you you do propping your bandwidth. So after several rounds, you know that, okay, your maximum sending rate should be at a certain level. Okay, that is the idea of congestion control. But actually, okay, that is the explanation we'll talk about later. But actually, how it works with to work with the pipeline design. Okay, we talk about pipeline right here, right? So here we have a window, right? So now, actually in TCP, the window is called congestion window. That is also certain bytes, okay, certain bytes. If you have a larger N, which means you have a larger congestion window, that means you can send more in-flight packet, which is a yellow packet, right, to the network. But if you have a smaller N, which has smaller congestion window, that means you have less in-flight packet on the internet, right? So basically, you can adjust the congestion window size, okay, to control your sending rate. Because if you have a larger congestion window, your sending rate should be larger. You have a smaller congestion window size, and your sending rate should be smaller. That is the idea, okay? And here we have a roughly sending rate formula right here, okay? The TCP sending rate should be close to this number, okay? The upper one is the byte, the congestion window in bytes. That means how many bytes you can send in flight when all the packets are yellow in congestion window, right? There's that amount of bytes, okay? And as we mentioned before in the pipeline design, right? In an RTT, in a round trip time, you should send all the yellow packet out, right? Because after one RTT, there should be the first ACK goes back. Then you can send the next segment out, right? So basically, your sending rate should be close to window size over RTT second. So that is your roughly RTP sending rate. So if you increase your sending congestion window, your TCP sending rate will be a little bit higher. And right here, the congestion window in TCP design is dynamically adjusted in response to the observed network congestion. So TCP congestion control, that means we should have a mechanism to continuously monitoring the current congestion level of the network, and we will adjust the congestion window size, that is the capital N, to decrease or to increase the sending rate. Okay, that is the definition. And here is the first mechanism we apply on TCP. We call TCP slow start. Okay. Okay, think about one thing right here. Okay. So A is the sender, B is the receiver. So at the first beginning, okay, right here, okay, I send one segment, okay, in bytes, it's 1 MSS byte. We send one segment out, and then I wait. At the first place, I don't send multiple packet. We don't use pipeline, right? At the first place, okay? So Act 1, right, comes back at this moment. So and at this moment, the original MSS is 1, right? And at this moment, I get 1 act. So I add 1 additional MSS at this moment. So currently, I have 2 MSS. So in this moment, I can send 2 data segments out. So that is the first round. We call it is the first round. Okay, first round. And second round, I have data 1 and data 2, okay? I send 2 segments out. And I will have Act 1 and Act 2. So at this moment, okay, originally, I have 2 MSS. It's from here. But when I receive 2 ACK, every time I receive an ACK, every time I receive an ACK, I add 1 MSS on congestion window. So currently, my congestion window has 4 MSS. That is the second round. This round, this round is a little bit larger than RTT because RTT only measure the time for one packet to A to B and the other packet back from B to A. But in this case, we have 4 packets, right? D1, D2, A1, A2. So this, in the second round, the time is a little bit larger than an RTT, but it's okay. Okay, we simply just call it the second round. Okay, so next round is very simple. The second round, it should be 8 MSS because I can send 4 packet out and I will receive 4 acknowledgement. So originally I have 4 MSS and currently due to the 4 acknowledgement, the current congestion window is 8. So you can see that we can incrementally increase the congestion window. And the congestion window will be doubled every RTT. So actually the name is slow start. That means we start from 1, 2, 4, 8, and so on and so forth, so on and so forth. But basically, as I mentioned right here, slow start is never slow because the increase rate is exponentially. Right? So next round is 16. Next round is 32. So by using that, we can incrementally increase our congestion window size. And in this case, we can increase our TCP transmission rate to test, to probe what is the current capacity of the current transmission capacity of the internet from A to B. So that is the initial start we call slow start. Okay, again, right here, okay, you have to okay, so take a look at this blue line right here, okay? So that is the transmission run. That is roughly equals to RTT, okay, roughly, okay? So that is the congestion window, CWND, okay? So initially at the first run, the initial is 1 MSS, right? For the second round, we have additional egg goes back. So it increased to 2, and then 4, and then 8. So that is after 3 rounds. The current congestion window size is 8 MSS. Okay, and here we introduced another concept right here. It is called SS threshold, which is right here. That is called slow start threshold. And think about one thing. You cannot increase the congestion window to a very, very high value, because that indicates you have a very, very high in-flight packet. You have a very, very high TCP sending rate. So it is not possible to increase this value unlimitedly, right? So in slow start mechanism, there is a slow start threshold, which, for example, right here, it is 8 maximum segment size. And after that, okay, every time when you receive an egg, you don't add 1 to the congestion window size. And at this moment, you add 1 over n. That means, for example, at this moment, okay, at this moment, we have 8 packets sent out, right? And there will be 8 acknowledgement will be sent back, right? But at this moment, because 8 is larger than the slow start threshold, so we don't add 1 on the congestion window. We only add, for example, right here, 1 over 8. Because you have you have 8 packet in-flight packet, so you will have 8 acknowledged packet, right? So each one increase 1 over 8 MSS. So in total, these 8 acknowledgement will in total add 1 segment, 1 maximum segment size to the congestion window size. So the next round, after you receive 8 acknowledgement, and each one add 1 over 8 MSS, and the total will be 9, right? Originally you have 8 and plus 8, 1 over 8, and at the end of this round, the congestion window will be 9. And at this moment, again, you can send 9 packets out, and you will receive 9 acknowledgement, and each one will add 1 over 9 maximum segment size to your congestion window. So the next round will be 10. At that moment, you have 10 data, 10 egg. Each egg will add 1 over 10 maximum segment. So on and so forth, so on and so forth. Okay. So before slow start threshold, we do slow start. Every time you receive an egg, you add 1 MSS to your congestion window. After slow start threshold, you add 1 over n maximum segment size each round, whenever you receive an egg. So at that moment, the increased slope will be linear, right? In this part, there will be linear compared to in slow start part, there will be exponential. Okay, So let's assume that at congestion window size 12 maxima segment, and you receive which I mean if timer timeout, okay, if timer timeout, then for this algorithm, what we call what is TCP Tahoe. Okay, TCP has several different versions, and this version is called TCP Tahoe. TCP Tahoe will decrease your congestion window to 1 if you experience an acknowledgement loss, a packet loss. And after that, okay, because that is a loss, right? So your slow start threshold also decreased to half of the congestion window size. Because originally it's 12, right? So if you experience a packet loss at 12, then your slow start threshold decreased to half of the congestion window, which is 6 right now. Okay, and your current congestion window will start again from 1, and so on and so forth. That means after that, you can increase your congestion window size exponentially until you reach your new slow start threshold and continue it linearly. So this blue line is TCP Tahoe. It describes how did you increase your congestion window by using slow start, and after slow start threshold, you increase your congestion window linearly until you experience a packet loss. Okay, that is called TCP Tahoe. And again, if you can do that, here is another black line right here. And actually, it should connect like this. And it is called TCP Reno. TCP Reno is another version of TCP. It takes another strategy that when you experience an loss, you don't have to decrease your congestion window to 1 MSS. You only need to decrease your congestion window to the slow start threshold, and then you can continue increase your your congestion window linearly. It's right here. That is just two different versions of TCP, and they take different strategy when they manage the congestion window size. Okay, that's it. That is two different versions of TCP right now. So that's it. Okay. So let's take a look at the real TCP congestion window, congestion control finite state machine, and that will be the end of our the end of this this hour. Okay. So please follow the step. Okay, I write some numbers right here, so you simply just follow these numbers. Okay, so the first one is initialize. Okay, at the first beginning, okay, when TCP starts, okay, it is at slow start state. Okay, so we have a congestion window size is 1 segment and the slow start threshold, and basically these two values is set by the operating system. Different operating system has different values, but it's okay. We simply just has some initial value right here. Okay, so step number 2 is right here. So at the slow start state, if new X is received by the sender, by the sender. Okay, and as we mentioned before, every time you receive a new egg, your congestion window increased one maximum segment size, right? So we simply just do so. And you can continuously receive new packet, new egg. And if possible, you can transmit new segments as allowed. Okay, so it's step number 2, 3, and 4. Okay, but eventually, your congestion window will be larger than the initial slow start threshold, right? So at that moment, step number 5, you go to another state named congestion avoidance. Okay, so right now you know that is called congestion avoidance. So the linear part right here, okay, actually it has name. It's called congestion avoidance, and the exponential part called slow start. Okay, so after that, when your congestion window size is larger than slow start threshold, then you go to the congestion avoidance state. Okay, so number 6. At congestion avoidance state, okay, when you receive a new egg, okay, right here, you simply just add, as we mentioned before, you simply just add 1/n maximum segment size right here. So if your current congestion window, you have to notice that in real TCP, when we calculate all those window size, they are all in bytes. Okay, so basically those numbers are all bytes. Okay, although we use 1 segment size, but actually it is a certain bytes. Okay. So for example, if you currently your congestion window is 8 segment size, 8 maximum segment size, and you add 1/8. 1/8 maximum segment size to the current congestion window. Okay, so actually, for example, if current is 8 maximum segment size, okay, so you add 1/8 right here, MSS right here, right, and you will have 8 X. So basically, you will transit at the congestion avoidance state 8 times because you will have 8 new X, for example. Okay, so that you stay in the congestion avoidance, okay, state. And the next one is number 7 and number 8. Sometimes when you send packet out, you send a pipeline, right? You can send a packet right at this moment, right? But sometimes packet comes, acknowledgement comes back, but sometimes you receive duplicate egg, right? So for example, sender receiver, and again, there should be some packet goes back, right? But maybe one of the packet is lost. So you receive egg 2, right? Egg 2. Because TCP use cumulative egg, so basically the egg 2 means we expect packet number 2, right? So that is the original egg, and this one is 3 duplicate egg. So basically you receive 4 eggs. So you have to continuously count how many duplicate egg at current state you receive. Okay, so number 7 and 8, you keep continuously counting the X. Okay, but right here, if you receive 3 duplicate X, that means there's something wrong with the network, right? Because apparently, because packet number 2 is lost, there's something wrong. But you still receive duplicate X. That means there's still some packet arrives at the router, but not all the packet arrives at the router, because one of the packet number 2 get lost, but 1, 3, 4, and 5 arrives at the router. So if you receive 3 duplicate X, then we transmit to another state called fast recovery, and at that moment you cut your threshold to half of the congestion window size, and current congestion window will be current slow start threshold plus 3. So for example, if the current so if the current congestion window is 12, and then the slow start threshold will become 6 if you receive 3 duplicate X, and the current congestion window will be 9. So when you experience 3 duplicate X, you slightly decrease your your congestion window, and you cut your slow start threshold to half of the current congestion window size. Because 3 duplicate X means there's something wrong, but not that bad. Okay, and after that, you retransmit the missing segment. For example, right here that is the D2 data number 2, and you enter a fast recovery state. That state means you keep monitoring the current status of the network, the congestion state of the network. Okay, so that is a state you keep monitoring. Okay, if you still receive duplicate X, that means okay, the following X still arrives at the sender, at the receiver, and at the sender. So I add 1 MSS. Okay, so we keep monitoring. Okay, so at fast recovery state, there will be 2 different situations. Number 1, if you receive new X, like step number 10, that means okay, the retransmit packet eventually arrives. Everything is fine, so I don't have to stay at the fast recovery state. Then I go back to the congestion avoidance state and keep linearly increase my congestion window. Okay, that is the good part. The bad part is that the left-hand side, at fast recovery state, if the timer times out, timer timeout indicate a worse congestion condition in the internet comparing to 3 duplicate. 3 duplicate only indicate that we have some problem, but maybe that is not severe. So we state at the phase recovery, see if new X will arrive like step number 10 or not like step number 13. So if eventually the timers time out, that means there's a severe congestion in the internet. So I simply just go back to the slow start state, and the current slow start threshold cut into half, and the congestion window goes to 1. That means we start over again. And of course, we retransmit the segment. So comparing to step 9 and step 13, step 9 indicates that we encounter certain congestion problem, but not severe. If we can recover, then we goes back to step number 10 and goes back to congestion avoidance. If congested get even worse, timers timeout, then that we goes to step number 13 and reset all the threshold and congestion window, and we start it over from slow start. Okay, that is the idea of TCP congestion control. Okay, and again I have to mention something about it's right here. That one, and yes. At any moment, at slow start and congestion avoidance, if you count 3 duplicate acts, no matter you are at slow start or you are at congestion avoidance, if you count 3 duplicate acts, you simply just go to fast recovery to monitor the current state. Okay, it is getting better or it is worse. Okay, and the next thing I will talk about is every time, at every moment, okay, at every state, you experience a timeout. That means something goes wrong and very severe. No matter you are at slow start or at your congestion avoidance or at fast recovery, every time you encounter a timeout, you simply just go back to slow start and start over again. Right? So you simply take a look at this part. They are all the same. Okay? And at any state, if you find duplicate act, you simply just count it to see if 3 duplicate act will be monitored. Okay? And that is the TCP congestion control mechanism that we can use a finite state machine to describe the congestion control mechanism. Make sure you follow all the steps, okay? So you can know what exactly each event means, and at different state, okay? When a new act received, okay, we have different scenarios right here, okay? So that's the one is called TCP cubic, but we will not cover all those materials. And think about one thing: when we adjust the TCP congestion control window, okay, and most of the time, okay, we will go up to the maximum window, and when we experience any packet loss, we cut into half, right? And we increase again, half, increase again, cut half. So basically, on the average, our TCP throughput, on the average, I mean, should be 3/4 maximum window size. That is an average, okay? That is just a discussion, okay? That is just an average, okay? So you can see that the blue dot line, there's another version of TCP congestion control, okay? That means when it cut into half, the increasing rate after cut in half, it can be higher, right? So it can recover much faster than TCP Reno or TCP Tahoe. It's just a concept, okay? We don't have any other detail about TCP cubic. We only talk about it can be faster to do such kind of recovery. So actually, you know, TCP has many different versions: Tahoe, Reno, cubic, or even some other new versions. All those different versions, they are trying to make the TCP performance even better than the previous version. Okay, so we simply just skip this one. Okay, and that's the one. That's the one is the notification. As we mentioned before, when TCP try to monitor, try to adjust the TCP congestion window. Okay, two mechanisms. One is three duplicate ACK. Okay, the other is the timer. So basically, TCP sender can monitor the congested level by itself, but in TCP and in the previous design, ideally, routers should tell the sender to increase its speed or to decrease its sending speed. But as I mentioned before, currently all routers does not support such kind of mechanism, so we simply just can skip this one. Okay, they will use certain bit in the TCP header and some bit in the IP diagram to indicate that the routers experience congestion. So TCP sender should slow down. But again, those mechanisms are not actually used in our IP network. Okay, so we simply just skip it. Okay. Okay. The next things we like to talk about is that think about one thing. We have two TCP connections, 1 and 2, and they share a router right here, right? So the capacity link is our BPS. Okay, we would like to discuss the fairness problem of TCP. Okay, think about one thing. 1 and 2, there are two TCP connections. Ideally, okay, each one of them should get half of the link capacity. That is what we call fairness. But TCP1 and TCP2, they are two different senders and receivers. And as I mentioned, router will not do anything about such kind of a communication or notification. So how TCP managed to that connection 1 and 2 to split to get half of the link speed. Okay, so take a look at this figure, but I have to draw it again. Okay, so I like to do something right here. Okay. Okay, we started from this point. Okay, so that you can see that is connection number 1, and y-axis the connection number 2. That is the throughput. Okay, that is the throughput. At certain time 0, okay, at certain time 0, okay, we can see that the connection number 1 has larger throughput. Okay, let's assume the R should be is 100 unit. Okay, for example, our BPS. Okay, BPS is okay. Assume the capacity is R BPS. Okay, and at time 0, connection 1. Okay, let's just assume that is 50. Okay, 50, and that is 10. At this time t moment, connection number 1 use 50 BPS, and connection 2 only use 10 BPS. Okay, because they have different congestion window size. They experience different congestions, slow start process or congestion avoidance. No matter what, at this moment, connection 1 use only 50%, use only 50 BPS, and congestion 2 use 10 BPS. Okay, at the next moment, T1, okay, since 50 plus 10 is less than 100, right? So they do not use all the entire RBPS, 100, right? So at that moment, the congestion window of connection 1 would increase because the buffer is not full. No packet is lost. So all of the data packet in R1 get all those acknowledgement. So at time T1, the connection 1, the sender, will increase its congestion window to certain number, right? For example, that might be 80, okay? At this moment, it could be 40, for example. So at T1, both of the sender of connection 1 and 2, they increase their congestion window size, right, to a certain level. But at this moment, 80 plus 40 is larger than 100, right? So part of the packet will be dropped by the routers. Basically, it looks like 1, 2, R, right? The network looks like this, right? But so at time T1, 120 bit per second traffic has been sent from 1, 2 to R. R will drop 20 bps data at time T1, right? Will drop. So think about one thing. In total, we have 120 bits per second traffic. 20 bits per second will be dropped. But think about one thing. By from the perspective of probability, packet from connection 1, okay, has higher chance to be dropped by the router, right? Because currently it has 80 bps and connection 2 has only 40 bps, and R has to drop 20 bps. So connection 1 has higher probability to drop packet, but connection 2 has smaller chance, of course, comparing to connection 1, to drop packet. So next moment, okay, next moment is right here. T2. Because connection 1 drop more packet, so at T2, its connection window size decrease a little bit more than the amount of connection window size decreased by connection 2. So at this moment, right here, maybe, again, maybe that is 30, and that is 55, something like that. So again, at time T2, the entire traffic is 85, which is less than 100, right? So at this moment, connection 1 and connection 2 will increase their congestion window size to another level at T3. And we can see that so on and so forth, so on and so forth. So basically, after several different rounds of increasing window size and decreasing window size, basically connection 1 and connection 2 will evenly share the RBPS. Because if you have more data to send and you have higher chance to be dropped, and you will decrease your congestion window more. If you have less packet to send initially, and when you increase your condition window, which is okay, and increase and increase. So basically, there are two these two connection. They will eventually will share the RBPS. So that is the reason why TCP has fairness, because the design of congestion window, they will decrease depending on the drop packet. So if you send too much packet, and you will experience more drop packet, and you will decrease your condition window size. And when you decrease your condition window size, the other one, which for example condition 2, they will increase their condition window size. So after several rounds, 1 and 2 will share the RBPS evenly. Okay, so that is the explanation. But basically, only TCP has fairness because UDP does not have any flow control or congestion control mechanism. So only TCP has fairness. So that's the last slide. Okay, so please take some time to review all those view graph. Okay, next week is final exam. Okay, make sure you go to the classroom to take the course, to take the exam. The exam here. Okay, we have some example right here. Okay, take a look at the midterm example. If I think it is quite helpful. And also we have homework number 4 this week, and they are all multiple choice. They are true and false questions, so it is more easily for you to review all those our course. So they are simply just some true and false question. You can simply just answer those questions on Google form. I believe that. And one important thing is that because we have midterm, right? So the due date of the homework number 4 must be earlier than midterm. So it will be at next Monday at noon. So that afternoon, the result will give you the answer of the homework number 4, so that you can review all those answers before you take the exam. Okay, so make sure you write homework, you send an answer before next Monday noon, and you review all those chapter 1, 2, 3, and don't forget to take the exam next week in the classroom. Okay, you have to go to the classroom. Okay, so that is